Hi there, welcome to Kung Fu Physics, where we are going to be working our way through the practice physics GRE problems. And today's problem is going to be off of the 2001 practice physics GRE exam. It is number 23. So if you want to flip to that and follow along, number 23, 2001. The problem looks something like this. Now, I am trying to get myself into the habit of scanning the answers before I attempt these problems, the first time that I see them. My reasoning behind that is, well, the answers are the final goal. So I need to know what my final goal is. I need to know what's available to me in those answers. And honestly, I want a scan of the answers and to see if there's any information present in those answers that will be helpful to me before I am influenced by the problem itself. We know that people that write the physics GRE write these problems a little tricky, so I want my unbiased opinion of those answers before they even are influence me at all with the problem. So I would look at these answers and I would see quickly that they are just a bunch of angles. The angles are in degrees, but it's no help to me whatsoever. Nothing stands out among the answers. So I would read the problem quickly, and after reading the problem quickly, I would decide whether I'm going to attempt the problem and commit the time or whether I'm going to leave it. So of course at Kung Fu Physics we're going to attempt all the problems at some point, but for right now we're going to do number 23. A particle is constrained to move in a circle with a 10 meter radius. At one instant, the particle's speed is 10 meters per second and is increasing at a rate of 10 meters per second squared. The angle between the particle's velocity and acceleration vectors is. Okay, so it's a classical mechanics problem, and it's very much a conceptual problem. The key to doing this problem fast, under 2 minutes, is to get a rapid picture in your head that is accurate of what's going on here. Translating what they give you in the problem into a rapid picture in your head. So we're talking about a particle that's going around in a circle. A similar type situation, if it's easier for you to draw the correlation, is a car going around a track. For me, that's an easy picture that's completely similar in this case. A car going around a track. So I'm imagining myself in this car, and if I am keeping constant circular motion, I would look at the speedometer in the car and it would not change. Whatever I set the speed at, if I set it at 10 miles an hour in the car, I could take the turns, follow around in a circle, and keep 10 miles an hour. That would be constant circular motion. That would be one physical situation. Now, I could also change my velocity and maintain a circle. In other words, I could sit in the car and I could push on the accelerator and I could increase the speed of the car. Still going on the track, still maintaining a circle, but I could increase the speed, or I could hit the brakes and decrease the speed as I went around. These are two physically different situations where something is moving around at constant circular motion and where something is moving around in circular motion but is accelerating. Now, and you can be picky about my words. Hopefully I'm trying to be very careful in these videos, actually. I do go through and edit them, and not edit so much. I mean, I redo them if I misspeak. When you talk about acceleration in a first-year physics class, even when the car is maintaining a constant speed and driving around that circular track, is the car accelerating? It is. As you are turning and maintaining a constant speed, you are accelerating because you're turning. So your velocity is changing. The magnitude of the velocity is not changing, but you're changing direction. So even if you are maintaining a constant velocity in this circle, you are accelerating. But for me, the physical picture of being in a car and actually pushing on an accelerator is a nice one. And so a long drawn out description of what you would have to process in just a couple of moments to do this problem fast. But you have a particle that's going around. Is it going around in constant circular motion? In this case, no, it is not. It's like I was in the car and I was pushing on the accelerator, because it tells us in the problem that at that instant the particle speed is 10 meters per second, but it is increasing at a rate of 10 meters per second squared. So that's the first thing. If you don't realize that that is happening and you don't have that accurate physical picture in your head of what's going on, there's a good chance that you could muck up this problem. So right off, I would translate that picture that I have in my head, that physical picture, to something I can solve the problem with. For me, I would make two quick diagrams, and they probably wouldn't be this detailed if you want the honest opinion. I'm doing this for the video, but the point C there is the center of the circle. The big black dot is where the particle is at, and those little dash dots, one dashed line, the straight line, represents the radius of the circle, and then the other one is sort of the path that the particle is following as it maintains a circular motion there. So I would make two pictures, one for acceleration and one for velocity. I know I want the angle between the net velocity and the net acceleration. So I'm going to start with velocity. I need the net velocity. I need to add, to get the net velocity, I need two components, the radial velocity and the tangential velocity. The first thing I should realize is there any radial velocity? In other words, is this particle moving towards or away from the center of the circle? And when I phrase it that way, you should immediately recognize that the answer is, of course, no. If the particle was moving in any way towards or away from the center of a circle, it wouldn't really be a circle, would it? Because the radius would be changing, and you wouldn't be constrained in that circular motion at that point. So this, the radial velocity, there is no vector here. There is no radial velocity. I have a tangential velocity. They give that to me in the problem, actually. And so I can draw in a tangential velocity here and label it. There's my tangential velocity. It's 10. I don't need the magnitude necessarily at this point. As it turns out, that is also the total net velocity. It's all tangential velocity. So I have that, and I can visualize here which direction that velocity is in. Now I move on to the acceleration. Is there a radial acceleration? Yes, there is. It should readily come to mind. This is the one equation that's kind of important to bring off the top of your head rather quick. So we would have a radial acceleration. It would be equal to the radial acceleration v squared over r. The velocity of our particle, the instantaneous velocity, right at that point, divided by the radius of the circle. So this is Kung Fu physics. We're going to move through this kind of quick. I'll talk more about units in other problems that we work. There are times when using units in these physics GRE problems is fundamentally important. Looking at units will oftentimes lead you directly to a correct answer in some of the physics GRE problems. Don't ever do this in your freshman physics class. But the velocity is 10, so I get 10 squared. The radius is 10. So the radial acceleration is going to be 10. I'm leaving the units off because we are trying to save time when we work these problems. We want to work these problems fast. Don't ever do that when you're actually working physics problems. And don't ever think for a second that I'm not imagining in my head when I see the radial acceleration equals 10, I'm not imagining it as 10 meters per second squared. I am, but for the point of this, you know, that's what it is. It's 10 squared over 10. The acceleration and the radial velocity is 10. What about the acceleration tangentially? Is it there? Yes. They don't tell you that. In the problem, they could have spelled it out easier. They could have said, and the particle is accelerating at 10 meters per second along its tangent in the same direction as its instantaneous velocity. They're not going to spell it out to you for like that. All they say is the particle's speed is 10 meters per second and it is increasing at a rate of 10 meters per second. You have to do the work and realize that what that means is if the velocity here is 10 and it's increasing at 10 meters per second, then what that also means to you is that the tangential acceleration also equals 10. All right, so I've been kind of long-winded in all of this, but I've got there. You've got the tangential acceleration is 10, the radial acceleration is 10. To get the net acceleration, you just add those vectorially. I would add those two vectorially. I don't need to get the magnitude of this by using Pythagorean theorem. I just know that the angle here is clearly going to be 45 degrees. 10, 45 degree angle. It's making a 45 degree angle with the net velocity. So I'm going to call this my net acceleration, or my total acceleration, A, and I compare it to my total velocity over there, V, and I can see that the angle between those two, if I imagine it superimposed there as well, it's 45 degrees. So I'd have to be confident, I'd have to remember back to my answers and know that I have a 45 degree angle there and confidently choose C as my answer. So to wrap up, if there was something that I was putting on the back of this card to study, I don't know that I would do this one, but if there was anything I would put, it would probably be something like this. The centripetal acceleration that will constrain a particle to move in a circle has to be that. Centripetal acceleration equals the instantaneous velocity squared divided by the radius of that circle. You can go back to your calculus to derive that if you like, if you want to refresh where that comes from. But that's a good one to remember. That has to be on the top of your head. As well as solving a conceptual problem like this, you have to develop an accurate physical picture of what is happening quickly. So that's all for problem number 23. And as always, I wish you the best of luck studying and taking the physics GRE.